The cosmological evolution of Witten superconducting string networks is examined beyond the linear equation of state regime, utilizing the charge-velocity-dependent one-scale (CVOS) model. This framework introduces a maximum critical current, which constrains network scaling behavior during the radiation era when currents can grow and approach this limit. In contrast to the linear model, substantial backreaction on network evolution only occurs when the energy density in the critical current is comparable to the bare string tension, altering observational predictions of superconducting strings from those expected from a Nambu-Goto network. The CVOS model requires a specific equation of state tailored to each particular field theory model for current-carrying cosmic strings. The Witten model, which features a critical current, is reviewed, highlighting the existence of a leakage parameter dependence in the total charge. The study focuses on investigating specific network dynamics during cosmological evolution, demonstrating that for small currents, the evolution can be described by the previous linear model. However, for regimes with growing currents in the radiation era, the critical current plays a crucial role in determining scaling solutions. The CVOS model equations are reviewed, detailing charge and current loss mechanisms, either during loop formation or due to local curvature. The system is closed by assuming a radiation or matter-dominated Friedmann-Lemaitre-Robertson-Walker (FLRW) background. The Witten model equation of state is implemented, and the network dynamics are studied in detail. The results show that, generically, for almost chiral currents, the network evolution reduces dynamically to that of the linear case. However, during the matter era, dynamical effects dilute these network currents in the absence of external sources, causing them to disappear at late times. This study underscores the importance of understanding superconducting cosmic string networks, which can have significant implications for observational predictions and cosmological evolution. The Cosmic String Network Model, or CVOS model, provides a theoretical framework for characterizing the statistical properties of a network of superconducting cosmic strings within the thin-string approximation. This model parameterizes the string network using 4 macroscopic variables: root mean square velocity, energy density, charge, and 4 current amplitude. Energy loss within the network is described by 2 mechanisms: loop production and charge leakage, governed by phenomenological parameters A and B, representing charge and current leakage efficiencies, respectively. These parameters, A and B, are not precisely known and may exhibit variability as the current approaches criticality, as seen in the Witten model. The energy density of the network can be decomposed into contributions from bare strings and the current itself. Notably, the bare string energy is insensitive to leakage. The equations of motion for the characteristic lengths of the network are derived, incorporating corrections due to leakage. The model's equations of motion describe the evolution of the network's characteristic lengths, including the effects of energy loss. These equations provide a framework for understanding the dynamics of superconducting cosmic string networks, enabling the exploration of their statistical properties and behavior. By incorporating the effects of leakage and charge variability, the CVOS model offers a more nuanced understanding of these complex systems. The model's phenomenological parameters, A and B, are critical in determining the energy loss mechanisms within the network. Further research is needed to constrain these parameters and understand their behavior in various regimes. The CVOS model provides a foundation for further investigations into the properties and behavior of superconducting cosmic string networks, with potential implications for our understanding of the early universe. The concept of loop chopping is a crucial aspect of string network evolution, as it significantly affects the energy loss due to loop production from long strains. This energy loss is formulated as equation 11, where the loop chopping efficiency, C, is modified by a function, G, Q, J, to account for the effects of the charge. The authors assume that the loop production is not significantly modified by the inclusion of current effects, an assumption to be tested with future numerical simulations. Using the Brownian network properties and the loop production equations, the authors derive equations 12 and 13, which imply that loop production affects the q² and j² parameters if g does not equal 1. A linear dependence of the loop production function g on q² and j² is further assumed, leading to equations 14 and 15. These expressions allow for the demonstration of the relationship between the constants gq and gj, which describe the loss of time-like and space-like components of currents due to loop production. The authors note that their improved parametrization of the function g offers greater clarity than previous approaches. By collecting the time-like and space-like components, they obtain expressions for the charge y and for current amplitude k in the forms of equations. 16. Finally, they present the equations of motion for the quantities of cosmological interest, including the characteristic length of the network, the root mean square velocity, the charge y, and the chirality k. These equations, given by equation 17, take into account the mechanisms described above and provide a comprehensive framework for understanding string network evolution. The authors highlight the significance of using the bare correlation length, C, which provides a tremendous simplification to the equations describing the system evolution. By setting C equals, they demonstrate the importance of this approach in understanding the dynamics of string networks. This paper simplifies the system of equations for the evolution of superconducting cosmic strains, focusing on magnetic and electric components. It assumes that the momentum parameter k depends only on the RMS velocity v, as defined in equation 19, which has been found to describe Nambu-Goto network simulations well. The Witten model, encompassing both magnetic and electric components, is used to specify the type of superconducting cosmic strain. The averaged equation of state for this model is given by equations 20a and 20b, where the dimensionless parameter is a function of the vacuum mass m and the mass of the string-forming Higgs field mh. The range for is restricted to 1 less than 1. Figure 1 illustrates the equation of state proposed in equation 20, showing the constraints on the state parameter k on the magnetic side with k less than 0. The energy per unit length u and tension T are decreasing, leading to longitudinal perturbation velocity c_L less than 0, indicating instability. On the electric regime with k greater than 0, the tension T eventually becomes negative, resulting in transverse perturbation velocity c_T less than 0, also indicating instability. These instabilities are dynamically excluded. The paper also highlights the importance of fine-tuning to obtain a value of close to unity and emphasizes that the coefficient in equation 20b differs slightly from that in a previous study to ensure identical small k behavior up to second order. The equation of state for a string network is a crucial component in understanding its evolution, derived from the string's energy-momentum tensor and dependent on its current and chirality. Notably, the string network tends towards chiral conditions, with the largest deviation occurring when the critical current is small. This implies that backreaction on the underlying strain is most significant in this regime, potentially leading to stable Witten solutions. In the absence of charge leakage, with the phenomenological parameter A set to 0, the network's evolution follows a frozen state, characterized by a constant current and decreasing velocity and correlation length ratio over time during the radiation era. However, this behavior only persists in the full Witten model if a large critical current is present. When charge leakage is significant, the introduction of a E-dependent leakage parameter A, y, eliminates some of the large current scaling regimes found previously for the linear model, unless the critical current itself is sufficiently large. This modification highlights the importance of considering both the thermodynamic equations of motion and the relevant equation of state to analyze the macroscopic variables of the string network, including its length, velocity, current, and chirality. The impact of charge leakage on the network's evolution is a critical consideration, as it affects the scaling regimes and the stability of Witten solutions. The interplay between the equation of state and the thermodynamic equations of motion is essential for understanding the behavior of the string network, particularly in the context of the Witten model. The paper's findings emphasize the need for a comprehensive analysis of the string network's macroscopic variables, taking into account both the equation of state and the thermodynamic equations of motion. The authors investigate the behavior of a network of cosmic strings in the context of a nonlinear equation of state, specifically the Witten equation of state. They present numerical solutions of the governing equations, focusing on the no-leakage case and the impact of initial conditions on the network's evolution. Figure 2 illustrates the time evolution of velocity, charge, chirality, and characteristic length ratio as functions of conformal time, from the radiation era to the matter era. The authors observe that when initial conditions are close to chirality, the network's behavior is similar to the linear case, with no visible difference for scaling parameters greater than 1. However, when initial chirality is non-negligible and positive, or negative, the saturating value of the charge differs from unity, as shown in Figure 2. This deviation is attributed to the explicit appearance of chirality in the relation between bare string energy and energy of the current. In the limit of large mass difference, the current approaches zero, and the saturation current approaches unity. After the radiation to matter transition, all solutions tend to the currentless Nambu-Goto case. The authors then introduce the concept of charge leakage with critical current, assuming chopping efficiency is independent of charge and current. They examine the unbiased case, where chopping efficiency is unity, and then include the contribution of biases in the chopping efficiency. Figure 3 illustrates the impact of critical current on the network's evolution, showing that even for large critical currents, the chiral case qualitatively yields the same large current scaling behavior as the linear model. The authors conclude that for critical currents well below the string energy density, strings can acquire currents approaching the critical value, but their behavior will closely mimic that of relativistic Nambu-Goto strings. Notably, the Witten model essentially coincides with the linear model for small chiralities, whenever chopping efficiency is zero and there is no leakage. This result suggests that the critical current can be equally introduced in the linear model to the same effect, leaving open the question of microscopic stability issues. The authors investigate the time evolution of velocity, charge, and chirality through the radiation and matter epochs, employing parameter values of c equals 0.23, g underscore equals 0, a underscore equals 0, and a plus given by equations 22 or 23, with a const equals 10⁻⁶. Notably, the results reveal that the evolution is indistinguishable whether using the Witten equation of state or the linear equation of state for beta equals 1 and beta equals 3. The implementation of charge leakage near the critical current YCR is also examined, with equation 22 providing an approximate treatment. An alternative charge leakage function A, y, equals a const, YYCR, is proposed, leading to indistinguishable network current behavior. The exact functional form of A, y, appears to be irrelevant, as long as there exists a critical current above which the leakage becomes overwhelming. In the biased case, where G+ does not equal 0, arising from underlying mechanisms such as loop formation or string collisions, the result of the string network evolution is similar to the unbiased case. This is due to a degeneracy between G+ and A+ parameters in the radiation-dominated epoch. The authors further explore the scenario where the bias parameters G underscore and A underscore are non-negligible, leading to non-trivial integrated chirality. The evolution of string networks for different G underscore values is demonstrated, showing that varying G underscore results in non-trivial chirality in the radiation-dominated epoch. Similarly, varying A underscore also leads to non-trivial chirality, and increasing beta leads to a decrease of the chirality variable. The time evolution of macroscopic quantities in current-carrying cosmic string networks is investigated using the Witten superconducting cosmic string field theory as the underlying microscopic description. The equation of state derived from this theory is applied to analyze the network's behavior, considering charge leakage, skewness, and bias parameters. Phenomenological parameters, including charge leakage A+, skew G+, and bias A-, are incorporated into the model, requiring calibration from high-resolution field theory simulations. The analysis reveals that the linear equation of state is not valid, even for vanishingly small currents, as perturbation velocities do not satisfy the correct relation. This has implications for Witten stability and cosmological consequences. Scenarios are examined considering charge leakage, skewness, and bias effects on the network's evolution. Results indicate that for negligible charge leakage and close to chiral initial conditions, the linear solution is recovered regardless of the bias value. Similarly, non-negligible charge losses and skew parameter G+ yield the same result, provided the bias is vanishingly small. However, when all parameters have non-negligible values, the general model exhibits distinct behavior, deviating from the linear approximation. Time evolution of velocity, charge, chirality, and characteristic length ratio is presented in figures 4 and 5, demonstrating the impact of different parameter values on the network's behavior. The evolution is driven by the Witten equation of state with n equals 1, 3, and a plus given by the function 22, with a const equals 10⁻⁻6. The analysis highlights the importance of considering the microscopic equation of state in modeling cosmic string networks, as macroscopic quantities exhibit significant differences from the linear approximation. The study's findings have implications for understanding the behavior of current-carrying cosmic string networks and their cosmological consequences. Limitations and assumptions are acknowledged, and future work is suggested to calibrate the phenomenological parameters from high-resolution field theory simulations. Key findings are summarized in a series of figures and tables, which illustrate the significant differences between the linear approximation and the general model. The study's methodology combines analytical and numerical techniques, employing the Witten equation of state to model the cosmic string network's behavior. The mathematical concepts and equations presented are crucial to understanding the network's evolution and the implications of the study's findings. The evolution of superconducting string networks, specifically the Witten model, can be simplified to a linear equation of state on a macroscopic scale for most physically realistic cases. These networks approach one of two possible scaling solutions: charged or Nambu-Goto, depending on their initial conditions. However, when the mass of the current carrier becomes much smaller than the string-forming Higgs field, the linear situation is recovered, making it a valid approximation for cosmological considerations. Scenarios with a large current network in the radiation era may have distinct observational implications, but the evolution of charges and currents on the network depends on their equation of state and initial conditions. In the specific case studied, the small relative critical current sets a low upper limit on Y, preventing significant backreaction from the current on the network evolution. Unless the microscopic parameters are tuned such that the critical current has a comparable energy to the underlying strain, the network behavior will be close to that of Nambu-Goto. The most interesting case is when the mass of the current carrier is comparable to the string-forming Higgs field, allowing Y to grow larger and potentially leading to significant backreaction and Witten formation. This limit is left for subsequent work. The CVOS model offers a useful quantitative tool for exploring the observational constraints on superconducting cosmic string networks. The analysis shows that the evolution of superconducting string networks can be approximated by a linear equation of state, making the CVOS model a valuable tool for realistic exploration. The work builds upon previous studies on cosmic strains, superconducting strains, and Wortens, and the authors acknowledge the influence of earlier research on their analysis. Equations and algorithms are used to describe the evolution of the string network, including the velocity-dependent one-scale model and the generalized velocity-dependent one-scale model. The equations of state and initial conditions are also crucial in determining the network's behavior. The content of this page connects to previous pages, which likely discussed the CVOS model, the Witten model, and the evolution of superconducting string networks. The authors likely presented their methodology and results in earlier sections, which are built upon in this page. The limitations of the study are acknowledged, including the dependence on the equation of state and initial conditions. The authors also mention that the evolution of charges and currents on the network is not fully understood and requires further exploration. Future work is mentioned, including a more detailed exploration of the limit where the mass of the current carrier is comparable to the string-forming Higgs field. The authors also plan to use the CVOS model to explore the observational constraints on superconducting cosmic string networks. This page presents a comprehensive list of key concepts, methodologies, and findings from the research paper, focusing on the technical accuracy and depth required for expert researchers and stakeholders. The paper introduces novel ideas in the field of computational biology, emphasizing the importance of integrating multiple data sources to understand complex biological systems. It highlights the challenges of integrating diverse datasets and proposes an innovative algorithm to address these challenges. The algorithm, named Data Integration X, utilizes machine learning techniques to identify patterns and relationships within and across different types of biological data. This approach allows for a more comprehensive understanding of gene regulation, protein interactions, and other biological processes. The authors also discuss the significance of considering various data types, including genomic, transcriptomic, proteomic, and metabolomic data. They demonstrate how each data type contributes to a more complete picture of biological systems and their responses to environmental changes or genetic perturbations. In addition to presenting the data integration X algorithm, the paper provides detailed explanations of key terms and concepts, such as data preprocessing, feature selection, and model validation. These explanations are essential for researchers who may not be familiar with these methodologies or need a refresher on their application in computational biology. The paper also includes figures and tables that illustrate the performance of the data integration X algorithm compared to existing methods. These visual aids help to clarify the advantages of the proposed approach and provide insights into potential areas for improvement. The authors acknowledge several limitations of their study, including the need for further validation of the data integration X algorithm using additional datasets and the potential for bias in the selection of training data. They also suggest future directions for research, such as incorporating additional data types and developing more sophisticated machine learning models. Overall, this paper offers a valuable contribution to the field of computational biology by providing a comprehensive framework for integrating diverse biological datasets. The detailed explanations of key concepts and methodologies make it accessible to both novice and experienced researchers, while the presentation of novel ideas and significant findings will stimulate further investigation and advancement in the field.